Ladies and gentlemen, is my pleasure to welcome you to the presentation on an analysis of a sensor switching approach for state estimation with applications to electrical power converters and energy storage systems. During this presentation, we'll start with a comparison of equivalent circuit models for those two systems, which on the one hand are fuel cell stacks comprising of multiple fuel cells that are electrically connected in series, as well as series-connected battery cells. For both of these systems will motivate the necessity for state estimation, which will then be performed by an unscented Kalman filter approach. The novelty of this presentation is an uncertainty-aware sensor switching strategy, which allows us to circumvent the property of a lack of full state observability. Finally, we'll have a look at simulation results before coming to conclusions and an outlook on future work. In a fuel cell stack, multiple fuel cells are electrically connected in series. As you can see on this slide, altogether we take into account a series connection of epsilon fuel cells. Each of these cells is characterized by its Nernst voltage as a directed voltage source, which depends on the gas partial pressure and temperature as the main influence factors. Moreover, the ohmic resistance RP takes into account activation as well as concentration losses, and the capacitance Cp for each of the fuel cells accounts for lag behavior and storage phenomena due to the double layer effect. Finally, ohmic losses in the interior of the fuel cell material due to the transport of charge carriers is accounted for by means of the series resistance Rs. From a system theoretic point of view, there exist two options for state space representations of the system. On the one hand, this is taking into account epsilon structurally identical state equations. On the other hand, it would be possible to derive a scalar system model where the sum of voltages is as the only scalar state variable. In order to perform state estimation that allows us to estimate and predict the operating conditions of each of the series-connected fuel cells, it is, however, necessary to take into account the individual state equations. This will also allow for the consideration of the variability of the individual cell parameters due to temperature and flow field inhomogeneities. However, if only the stack voltage as the voltage sum over all the individual electrically series-connected cells, as well as the terminal current as the control variable are available as measurements, this system model does not possess the property of full state observability. This is similar to the scenario in which we take into account state estimation of a series-connected branch of multiple battery cells. There we take into account, again, epsilon battery cells that are series-connected, where each of these cells is characterized on the one hand by the open circuit voltage as a directed voltage source that depends on the state of charge, the temperature of the battery cell, as well as its state of aging. The state of charge is accounted for by means of a normalized quantity, where 0% means a fully discharged battery and 100% a correspondingly fully charged cell. Dynamic effects are accounted for by RC subnetworks in the equivalent circuit model, where we take into account during this presentation two different time constants with small and large values. Those time constants, as well as their dependencies on the state of charge, can be identified with the help of impedance spectroscopy. Moreover, ohmic losses, which represent an instantaneous voltage drop for step-like changes of the terminal current, are included with the help of the series resistances Rs in each of the cells. When deriving a set of state equations for the series-connected branch of battery cells, each of the cells is being described with the help of the state vector with three entries, where the entries are the state of charge and the two voltages across the RC subnetworks. The corresponding state equations are then being derived in the help of a quasi-linear representation, where both the system matrices depend internally on the state of charge. Especially the time constants are denoted here on the slide as the product of the capacitances and resistances in the equivalent circuit. When performing battery management, it is necessary to estimate the state of charge of each of the individual battery cells. This is especially crucial to prevent low discharging and overcharging of the cells, because such phenomena like low discharging and overcharging may lead to dangerous operating conditions with the risk of internal short circuits in which a battery cell can even catch fire. Moreover, for the practical implementation of battery management systems, it is crucial to minimize the amount of required voltage measurements and to provide state estimates that can be used reliably in order to perform active equalization of both the state of charge or the voltages of the individual cells connected in series. However, as in the case for the fuel cell stack that we have considered at the beginning of this presentation, the series connection of multiple battery cells lacks the property of full observability if only the terminal current as the control variable and the sum of all the terminal voltages are available as the measured quantities. In order to implement state estimation procedures, it is relevant to account for uncertainty. Uncertainty arises on the one hand in the state equations in the form of uncertain parameters. Those are all of the equivalent circuit parameters like the battery capacity and all the other equivalent circuit quantities. Those uncertainties are being represented in the presentation by means of uniformly distributed multiplicative uncertainty, which is set to 5% independently for each of the parameters during this talk. Those uniformly distributed uncertainties are being approximated by means of a normal distribution with identical variance, which is denoted here in the slide. Additionally, we account for Gaussian process noise acting on the state equations after the temporal discretization in additive. Finally, actuator and sensor uncertainty is being taken into account, which are being described with the help of Gaussian distributions, on the one hand for the standard deviation of the terminal current with an uncertainty of 10 milliamperes and a standard deviation of 1 millivolt for the corresponding voltage measurement. When performing state estimation, we are working on a discrete time implementation of an unscented Kalman filter. The state prediction is then being performed in a classical manner where we predict the corresponding probability density function in the form of an approximation by means of a Gaussian distribution. For that purpose, we're determining sigma points for all of the state variables, as well as for all the uncertain parameters mentioned before, as well as for the uncertain terminal current. During the innovation step, there exist two options. One option is to measure all the terminal voltages of the series connection of battery cells. However, this is quite costly and can be avoided by measuring only a single terminal voltage, where the cell to be measured is determined with the help of an investigation of the estimation uncertainty resulting from the prediction step. There, we're requesting a voltage measurement for the battery cell that has the largest uncertainty in the estimated state of charge. Further options that are not being investigated during this talk are cyclic switching between the measurements or random sensor selection approaches. It should be pointed out in this slide that we do not necessarily measure terminal voltages at the same points in time as we're performing the state prediction. We have included a scaling parameter, capital M, that allows us to specify an integer multiple of the discretization step status of the state prediction as the corresponding measurement sampling time. Now let's have a look at the corresponding results. On this slide, we are summarizing the estimation accuracy if all terminal voltages are measured at the same point in time. What you can see on this slide is that for a selected battery cell, that's in this case the battery cell number 4 in a series connection of 8 batteries, an accurate state reconstruction is possible despite the uncertainty in the system parameters as well as the uncertainty and noisy measurements of both the terminal current and the terminal voltages. The uncertainty is further investigated here, where we take into account the uncertainty by means of a 3 standard deviation tolerance bound for the state of charge here on the left-hand side, in the middle for the terminal voltage at the RC subnetwork with a small time constant, and on the right-hand side, the terminal voltage at the RC subnetwork with a large time constant. For all of these 3 state variables, the corresponding estimates are consistent with the corresponding 3 standard deviation points. Now let's switch to the uncertainty-aware sensor selection. As mentioned before, we're measuring only the terminal voltage at one point in time for the cell that has the largest uncertainty in the predicted state of charge. When doing so and synchronizing the discretization of both the requested measurements and the discretization of the prediction model, we're obtaining the uncertainties summarized on this slide. What you can see that all of those 8 series-connected battery cells are being estimated accurately, both from the points of view of the state of charge and the voltages at the RC subnetworks. What you can detect additionally is that only a negligible deterioration of the estimation accuracy occurs in comparison with the result where all the terminal current voltages were measured simultaneously. Moreover, when increasing the discretization step size in which the innovation steps are being carried out, only a further small increase of the uncertainty occurs. That means our estimator is quite insensitive against a reduced rate of the execution of the innovation steps. It should be pointed out at that position that we have managed, with the help of the uncertainty-aware sensor switching approach, to reduce the requirement of 8 voltage measurements to a single voltage measurement. That means we have saved 87% of the required sensor effort. Now let's come to conclusions and an outlook on future work. What you have seen during this presentation is a robust state estimation approach based on a sensor switching technique that can be applied for fuel cell stacks and series-connected battery cells in an identical manner. This approach allows us to circumvent the problem of a lack of full observability that arises in cases when only the sum of all the terminal voltages over the series-connected branch of cells is available as a measured quantity. Moreover, you have seen that the estimates are robust against parameter uncertainty, which have been represented by means of random variables during this talk. Finally, insensitivity against the choice of the rate of the execution of the innovation step has been presented. During future work, we want to include the corresponding estimation procedure in battery management systems and to evaluate those procedures in an experimental manner. Finally, we would like to exploit the corresponding estimates to perform active balancing of the state of charge of the series-connected battery cells, or alternatively, to balance the terminal voltages. Finally, extensions towards set-based uncertainty representations with the help of interval observers will be investigated. For further related publications, you can have a look at the list of references given on the slide. Thanks a lot for your attention.